So what if I told you that five incredibly different scientific frameworks, and we're talking radically different fields here, are all secretly pointing to the exact same underlying geometry of reality?
And say you've been reading that massive synthesis report that's been going viral lately.
Yeah, exactly. I mean, for you listening, imagine pulling a thread in the mathematics of some billion parameter neural network,
Yeah.
right? And suddenly you unravel a mystery in quantum gravity. That is the really seductive idea circulating right now.
Yeah, it's definitely provocative.
Very. I mean, you've got the holographic principle from string theory, Stephen Wolfram's computational hypergraphs, Max Tegmark's mathematical universe hypothesis, the latest learnable manifold stuff from DeepMind, and it's all anchored by this groundbreaking AI paper out of Johns Hopkins.
Right.
And they all seem to be whispering the same secret, that the universe we observe, the physical laws we experience, is actually just a highly compressed geometric shadow of a much larger reality.
Yeah, it's arguably one of the most ambitious synthesis attempts we've seen in the last decade, I'd say.
For sure. So today we are doing a deep dive into this report. It's titled A Low-Rank Computational Geometry of Reality. And it comes with these three very intense infographic panels.
Which is where things get a bit messy.
Oh, absolutely. So our mission today, for you listening, is to act as an audit. The base report is actually a really disciplined, intellectually honest piece of speculative science writing.
It really is.
But the visual panels introduce some dangerous overreaches. So we're going to deconstruct it all. We want to separate the mathematically verifiable anchors from the highly speculative leaps.
Because we need to see where the rigor actually holds up and, frankly, where it completely breaks down.
Right. So let's start with the core motif. Before we rip into the details, we really need to decipher what this synthesis actually claims, because the internet has taken this idea and just run with it.
Oh, the memes have been out of control.
Seriously, like you see headlines screaming reality has a low matrix rank, basically implying the universe is just a compressed flat file, like a low-res JPEG.
Yeah, and we have to clarify right away that the rigorous report explicitly insists it is not saying reality has a low matrix rank in a literal simplistic sense.
Thank goodness.
Right. Because conflating holographic dimensions in string theory with matrix rank in machine learning or algorithmic description length, if you just pretend those are all the exact same mathematical quantity, it sounds profound, but it's mathematically empty.
It's just a buzzword soup at that point.
Exactly.
Yeah.
The true motif across all five of these frameworks is actually a three-step pattern.
Okay, walk us through it.
So first, you have a vast microscopic possibility space. Then step two, out of that vast space, a stable, observer-accessible effective sector is carved out.
Okay, so it gets narrowed down.
Yes. And step three, that effective sector is what gives rise to the low-dimensional geometry, the physical laws, and the predictions that the observer actually experiences.
Right, okay. Let me try to translate this for the listener with an analogy.
Go for it.
So imagine a really high-resolution 3D video game, right? You've got billions of lines of code, the physics engine, the rendering engine, the memory allocation, that's your vast microscopic possibility space.
The underlying mechanics.
Yeah, the mechanics. But as
Yeah.
a player, you're not tracking memory addresses or lines of code. You just need to know that if you press the A button, your character jumps.
Right.
If you accept a tiny bit of pixelation or like a minor predictive distortion, the actual number of variables you need to successfully navigate that game, your speed, your health, your position is incredibly small compared to the code.
That's a perfect way to look at it. What survives coarse graining, what actually makes it through to the observer, is not the raw astronomical data of the universe. It's a stable equivalence class.
The stable equivalence class.
Yeah. High dimensionality belongs to the space of descriptions, right? The billions of lines of code. But low dimensional geometry belongs to the space of invariance, the things that actually matter to the observer.
Okay, that makes sense. And the report formalizes this with a specific equation, right?
It does. It introduces this master equation. It's d sub obs, which is a function of epsilon and the observer O.
Hmm.
And that is strictly much less than d sub micro.
Okay, let's break that down for people who don't speak math. The D micro is the combinatorial dimensionality of that underlying space, the billions of lines of code, or in reality, trillions of particles.
Right. And the O is the observer, basically defined by the specific operations or measurements they can actually make.
And the epsilon?
Epsilon represents an admissible predictive distortion. It defines how much loss of resolution or error the observer is willing to tolerate while still being able to function.
So how much pixelation I can handle before I can't play the game anymore.
Exactly. And so d sub obs is the observer's effective dimension, the number of variables they actually need. The equation is basically saying that if an observer is bounded by operational limits, their effective dimension is orders of magnitude smaller than the microscopic dimension.
They call it the low-rank observer principle, right?
Yeah. It argues that stable observers encounter reality exclusively through these highly compressed effective sectors.
But let me push back on this a little bit. Is this just epistemology or is it ontology?
That's the big question.
Because it's one thing to say, humans have limited primate brains, so we have to compress a complex universe into simple laws just to survive. That's epistemology. That's just how we learn.
Right, our cognitive bandwidth limit.
Yeah. But it's a massive leap to claim that reality itself, like the literal curvature of space-time, fundamentally organizes around this bottleneck. That physical law is just the geometry of what survives the bottleneck.
That pivot is exactly where the synthesis goes from a neat philosophical idea to a grand theory of reality. And to see why they make that leap, we have to look at the load-bearing pillar of this entire project.
Which brings us to the AI data.
Exactly. We have to look at the Kashik et al. Paper. This is a very real, very recent AI preprint from Johns Hopkins, December 2025.
This is the part that genuinely blew my mind when I was reading the source material for this deep dive.
It's incredible research. It's titled The Universal Weight Subspace Hypothesis. And the scale of it is just staggering. They didn't just test a couple of toy models. They looked at over 1,100 AI models.
Right, and not even the same kinds, right?
No, completely different architectures. 500 vision transformers, 500 fine-tuned language models like Mistral 7B LoRaWAN, massive LAMFI 8B models, and older stuff like ResNet 50.
So they're looking at image processors, text generators, everything.
Yeah, they wanted to see the geometry of how these models actually learn.
Okay, so how do they even measure that? I mean, these models have billions of parameters.
They do. So they define something called a population second moment operator.
Okay, you're going to have to explain that one.
Basically, they take the gradients of the model's loss function, so how the model tweaks its internal weights, to get better at a task across a massive distribution of natural data. And they calculate the covariance matrix of those gradients.
So it's kind of like looking at the footprints of where the AI is spending its energy.
Yes, exactly. If the parameter space is a billion-dimensional landscape, the second moment operator tells you which specific directions in that landscape the network is actually moving along to solve problems.
Okay, got it. So they map all these footprints out, and what are they looking for?
Mathematically, they were looking for an eigengap.
An eigengap?
Yeah, it's a sharp drop-off in the importance of different data directions. If you break that massive matrix into its principal components, you can rank them by how much variance or information each direction captures.
So an eigengap means what exactly?
Means the first few directions capture almost all the information, and then the values suddenly fall off a cliff, like a massive drop. Everything after the gap is basically noise. It contributes practically nothing to the model's performance.
And this is the crazy part. Because across these 1,100 models, with billions of parameters, a massive amount of the variance collapsed into 16 or fewer directions.
16 or fewer, yes.
I mean, that is wild. They're effectively operating in a tiny 16-dimensional subspace to solve these insanely complex natural tasks.
It's a stunning empirical validation of that core motif we talked about.
Right.
The neural network's parameter space is the vast microscopic possibility space. The optimization process creates an observational bottleneck.
And then that 16-dimensional subspace, the stuff before the eigengap, that's the low-dimensional effective geometry.
Exactly.
But, all right, I have to jump in here with some nuance because this is where the internet hype machine goes off the rails.
Oh, absolutely. AI proves the universe is 16-dimensional.
Right. You see that on Twitter and you just roll your eyes. But this is where I have to give major credit to the deep research report we're analyzing. It is a model of good science communication because it actively corrects those meme-ified overclaims.
It really does. The report is very careful to flag that the Kashik paper does not claim a universal 90 to 95% variance capture across every single model in existence. And it certainly doesn't claim 16 to 32 dimensions is some universal mathematical law of nature.
And crucially, the Kashik paper is architecture specific, isn't it?
Highly architecture specific. You cannot currently take the subspace of a ResNet processing an image and directly compare it to the subspace of a vision transformer processing the exact same image.
Because they're wired completely differently inside.
Exactly. A transformer uses self-attention, looking at the whole image at once in patches. A ResNet uses convolutional layers, building up features locally. Their internal vector spaces are entirely incommensurate. You can't just map one onto the other.
So the empirical reality here is that optimization drives models into small, shared spectral sectors as long as you stay within a given architecture.
Correct. It doesn't prove all intelligent systems converge on a literal 60-dimensional basis. And the report's restraint in stating that is exactly why the base text is so intellectually honest.
Okay, so we've seen where the synthesis is really well grounded in empirical AI data. It's rigorous. But now we have to look at the theoretical physics side of this grand unification.
Which is where things get a bit more speculative.
Yeah. Let's talk about the Wolfram caveat. Because Stephen Wolfram's physics project is a major theoretical pillar of this synthesis, and it doesn't really have the same rigorous foundation.
No, it doesn't. So, briefly, Wolfram's contribution to this synthesis is centered around the idea of discrete computational hypergraphs. He posits that fundamentally, the universe isn't continuous space-time, but a constantly updating network of nodes and edges governed by simple algorithmic rules.
Right, and the synthesis report connects this to the low-rank motif using Wolfram's concept of causal invariance.
Right. So if you have a massive graph updating, there are countless different possible orders in which those updates could happen. Causal invariance means that no matter what order the updates occur, the final causal graph, the history of what caused what, remains identical.
And the report draws this brilliant parallel, right? It links causal invariance to discrete general covariance.
Yes, like gauge reduction in standard physics. It essentially factors out the redundant microscopic histories, leaving behind a stable, invariant, effective sector.
It's a gorgeous mathematical analogy. It really is. But I have to intervene here to pump the brakes for anyone listening. We cannot mistake this for established consensus physics.
Definitely not.
There is severe pushback from the mainstream physics community on the Wolfram project. I mean, if you look at Adam Becker's Scientific American article from May 2020, it's brutal.
Yeah, the critique from MIT's Daniel Harlow in that article is particularly damning. Harlow points out that mainstream physics theories like quantum electrodynamics or general relativity, they confirm predictions to 1 part in 10 billion.
Insanely precise.
Right. But Wolfram's model, it has produced 0 novel quantitative predictions. Harlow notes its successes are, at best, qualitative. He can vaguely mimic things we already know, but it can't predict anything new with math.
And Scott Aronson from UT Austin, he's a theoretical computer scientist. His critique was even sharper. He called Wolfram's framework an infinitely flexible philosophy.
Because the hypergraphs and the rewrite rules are so unconstrained, you can retroactively tweak them to fit literally any observed physical law.
Yeah, Aronson had this brilliant analogy. He said, treating this as a theory of physics is like saying, well, if we suppose a rabbit comes out of a hat, then remarkably, a rabbit comes out of a hat.
A theory that can fit any possible outcome predicts no specific outcome. So, treating the Wolfram Ruliad as a co-equal, established framework next to something like Maldaceno's ADA-CFT correspondence, which is mathematically rigorous and heavily cited, is probably the single biggest missing caveat in the broader internet discourse about this synthesis.
Absolutely. The analogy's neat, but it's not verified physics. And to be fair, the base text report is pretty disciplined about hedging these things. It's careful. But
Then the author decided to make those 3 infographic panels.
the panels, this is where the discipline just completely slips. Let's do an audit of these panels from the most solid to the most wildly speculative.
Okay, let's start with the solid ground. That's panel B.
Panel B, entanglement and gravity.
Right. This panel traces a very real, very legitimate lineage in theoretical physics, linking relative entropy and modular Hamiltonians to the emergence of spacetime.
So saying space-time is built out of quantum entanglement.
Exactly. And they cite the real giants here. Ted Jacobson in 1995, who basically derived Einstein's equation of state just from thermodynamics.
Showing that gravity might just be an emergent statistical property like heat.
Yes. And then Mark van Ramsdonk in 2010 and Thomas Faulkner and his colleagues around 2014 and 2017. This is all robust theoretical physics.
There's a specific analogy in the sources for this that I want to share with you listening because it helps explain the relative entropy part of the panel.
The card deck analogy.
Yeah, the card deck. So relative entropy is a measure of distinguishability. How easy is it to tell 2 quantum states apart? Imagine 2 mixed up, shuffled decks of cards. If you pull one card from each, it's really hard to tell which deck is which, right? They're very indistinguishable. That's low relative entropy.
Right.
But if one deck is all hearts and the other deck is all spades, you pull one card and boom, you instantly know which deck you're holding. That's high relative entropy. They're highly distinguishable.
And what Jacobson, Van Ramsdorff, and Faulkner showed is that the equations governing this distinguishability, this equilibrium of information, are mathematically isomorphic to Einstein's equations.
The distance between 2 points in space is just how distinguishable their quantum states are. That is so cool.
It is. And Panel B captures this perfectly. This solid, established physics.
Yeah.
Then we get to Panel C.
Panel C, the 5 candidate functionals. This is where we start seeing the overstatements.
Yeah. So Panel C lists 5 mathematical tools, things like spectral action from Chamsdien and Kuhn, quantum Fisher information, optimal transport.
Which are all real mathematical frameworks. Right?
Oh, absolutely. Optimal transport, for instance, is fascinating. Mathematicians like Mondino and Sewer use it to study the Ricci curvature of spacetime. It's very real math. The catch is what the panel claims these tools do.
Right. The panel claims that extremizing these functionals reproduces Einstein's equations.
Which is a major overstatement.
Can you clarify that? Like, what's the exaggeration there? Does it not unify the theory?
No, it's not a unified theory yet.
Yeah.
These tools only offer partial derivations. For example, that work by Faulkner we just praised. It only gives you linearized equations of gravity.
Okay, so it doesn't give you the full nonlinear Einstein equations from scratch.
Exactly. And Mondino and Sewer's optimal transport work. It reformulates general relativity in a new mathematical language, but it assumes the cosmological constant and the energy momentum tensor are already given.
Ah.
It's a translation of existing physics, not a derivation of physics out of thin air.
And it ignores the failures, too, right? Because I recall the spectral action functional actually made a prediction about neutrinos.
Yes, it predicted neutrinos would be completely massless.
And they aren't.
They aren't. The Super Kamiokande Observatory proved they have mass. So presenting these functionals as if they just neatly reproduce reality ignores that they have produced falsified predictions.
Wow. Okay, so Panel C overstates the math, but Panel A is just wild.
Panel A is the Eigengap Big Bang.
Yeah. What if the Big Bang wasn't an explosion of matter in space-time, but the exact moment a mathematical eigengap opened up, solidifying a stable geometry out of pre-geometric information?
It is a brilliant, stunning visual. But I have to state plainly, this is a completely novel, unpublished extrapolation.
Yeah.
Now, geometrogenesis, the idea of space-time condensing from a pre-geometric state, and there's a real concept studied by physicists like Daniele Arrighi.
Right.
But grafting Kaushik's neural network eigengap math directly onto the origin of the universe, there is absolutely zero peer-reviewed analog for that.
The panel tries to soften it by calling it a thought experiment, but when you put it in a slick graphic next to real physics, it blurs the line. We have to call it what it is: pure, brilliant, but entirely unsupported speculation.
And that leads us to the fundamental editorial critique of these infographics, the danger of fake precision.
The math washing.
Yes.
I mean, you look at these panels, and Panel A ranks a cosmological bounce as being most structurally aligned with naturalness. And then Panel C actually slaps literal plausibility percentages on these open physics questions.
He says relative entropy has a 35% plausibility and optimal transport has a 5% plausibility.
How do you even calculate that? You can't. That's just putting numbers on a philosophical guess to make it look like hard empirical data. It's math washing.
It's an editorial failure, not just a graphic design choice. By assigning exact percentages and league table rankings to deeply unresolved metaphysical problems, the author basically invites easy dismissal from real physicists.
It totally undermines all the careful hedging that made the base text report so credible in the first place.
Exactly. If you want to evaluate theories qualitatively, call them highly speculative or promising. Don't slap a fake 35% metric on it.
Yeah. But look, we spent a lot of time critiquing the wild speculations here. I don't want to just tear it down and leave it there, because the synthesis actually offers something that most philosophical theories of everything totally lack.
Falsifiability.
Yes, a way to actually prove it wrong in a lab.
Right. The report proposes concrete experiments, which elevates this from dorm room metaphysics to a legitimate research program.
Walk us through the first experiment, the cross-architecture spectral comparison.
Okay, so earlier we said you can't compare the internal wiring of a transformer to a CNN.
Right, they're incommensurate.
So this experiment proposes bypassing the internal weights entirely. You take radically different architectures and you map them into a common function space, based purely on how they process standard data.
Oh, interesting.
You test them on standard inputs, construct the second moment operator based on their external outputs, and ask, do they form the exact same dominant spectral projectors?
Do they agree on the geometry of the task, even though their internal brains are completely different?
Exactly. If they do, that's massive evidence for a universal low-rank geometry. If they don't, the theory takes a huge hit.
Okay, and what's the second test?
The second test involves observer resource scaling plateaus.
Right. This is the one that really gets me.
It's fascinating. You create an artificial observer in a simulation, and you slowly increase its computational budget. You give it more memory, better sensors.
You increase its bandwidth.
Right. And you measure the effective dimension of the reality it perceives, the d sub obs. Now, you would assume that as the observer gets smarter, the dimensionality of its reality grows smoothly, right?
Yeah, you'd think it just slowly sees more and more of the microscopic truth.
But the low-rank hypothesis predicts the opposite. It predicts the observer will hit hard plateaus.
A plateau. So no matter how much you turn up the dial on its processing power, the physical laws it experiences stay exactly the same.
Yes. And if that happens, it means objective macroscopic reality is actually just a universality class.
Meaning different observers, even with entirely different brains or computers, will all agree on the exact same physical laws. Not because the universe is fundamentally that way, but because they share the same mathematical limits of that plateau.
Exactly. But if there are no plateaus, if the physics just change chaotically every time you tweak the observer's memory, then the theory is falsified. The low-rank geometry isn't real, it's just a subjective hallucination.
Wow, and that is what makes this real science, the fact that they laid out experiments that could destroy their own beautiful theory.
That's the hallmark of intellectual honesty.
It really is. And I want to leave you, listening, with the final, somewhat provocative thought to chew on. Building on this whole observer plateau idea,
Let's hear it.
if physical law, if space-time itself, and cognitive generalization are all just the geometry of what survives this mathematical eigengap bottleneck, what happens if our biological evolution shifts our cognitive threshold?
Oh, wow.
Right, like, are the laws of physics we observe today just an artifact of the exact amount of computational limit the human brain currently possesses?
That's a staggering question.
If we merge with machines, if we use neural interfaces and radically change our bandwidth, do we get pushed off our plateau? Does the fundamental geometry of the universe change with us?
The post-human physics.
Exactly. Something to think about. Thank you so much for joining us on this deep dive. I know the math was heavy today, but it is so crucial to keep questioning the nature of the information we consume, especially when it comes wrapped in slick infographics.
Absolutely. Stay skeptical.
Keep questioning, and we'll catch you on the next deep dive.